Welcome everyone. This is the first session of 2026. I know Mike's absolutely chomping at the bit to tell us what's been happening over the last couple of months. For those who don't know me, my name's Dylan. I'm the co-founder of Digitalent. Outside of helping companies scale their product and engineering teams, we've made a good push to help build communities in certain areas, AI being a huge one for us. Obviously AI is changing every single day and people are learning every single day. We wanted to create an environment where everyone can share insights, challenges and successes. Mike and I have been working on this for probably a year and a half or so, and I think we've brought some really interesting creative people together that's created some really positive outcomes for a lot of people. So it's been an absolute pleasure to host. Mike Nedelko, he's one of our community members, an expert in the AI space, a great presenter, someone you can rely on for advice and support. He's always there for you when you need him. He's going to present for the next kind of 40 to 45 minutes or so, and then it will give everyone a chance right at the end to engage and ask questions if they want to. So Mike, I'm going to leave it to you, mate. I know you've got lots to talk about, so take it away.
Exciting. Well, thanks everyone for joining. We obviously really appreciate it. Thank you very much, Dylan, for once again convening such a wonderful group of people. I myself am a product leader and CPO. I'm a technical product manager. I've been an AI and an ML enthusiast since about 2008. And I have had the opportunity to maintain that passion through my work, where I manage product and engineering teams that are predominantly focused on delivering AI and machine learning driven value propositions, helping companies both with their journeys towards more AI-driven value creation, as well as their products. Some of the team members that I get to work with in that work are also here today. So shout out to Fatma and the lead and some other folks that I get to work with, which is absolutely delightful, right? Now, if you are an AI researcher yourself, if you're working in the AI and ML space, there's a chance that you may know about the things that we're going to talk about today. You might not have heard about them in that particular sequence, which still provides value, of course, but obviously that's your job, so you are probably tuned into that space. If you're not an AI researcher, please do not dismay. What we're going to do here is we're going to take what I believe are the most prevalent paradigms that we've sort of seen evolve in this AI space over the last 30 to 60 days, sort of like since the beginning of the year. And then we're going to weave a story around it that lets us sort of understand and get a feel of where the AI space is going from a technology perspective, but also from a product perspective. So as always, what I'm saying at the beginning of these presentations is what we're not going to do is talk about every single paper that has been written over the last couple of weeks and months, and we'd still be here by the end of next week if that was the case. But nevertheless, I think what we're going to do today is we're going to dive into a few papers that will help us put at least some aspects specifically around agentic AI innovation into perspective. And I can say without exaggerating that the last 2 months have been absolutely insane in the AI and R&D space. And the most prevalent news we've all been hearing about over the last couple of weeks has been OpenClaw. Now, for those individuals who are in engineering, I know you're quietly rolling your eyes right now. I was too. And I can guarantee to you that this presentation isn't necessarily about OpenClaw itself. And it is not going in the direction that you might expect it to go now that I have mentioned it. We're deliberately not going to follow the hype that everyone has been pursuing. We are going to explore the subject of skill-based, self-evolving AI, specifically agentic AI today. And OpenClaw just needs to be mentioned in a particular capacity in that way. So for those not in the know, OpenClaw is a free open source AI agent. It was developed by an Austrian gentleman called Peter Steinberger. It runs on your own hardware, right? Or you can also deploy it anywhere else. But the way it works is that you can ask it to develop its own skills, edit its own code, and even schedule its execution, right? I'm just very quickly, for those that are not in the known, just to make this a little bit relatable, show you a quick Telegram chat that I had with my bot about 15 minutes ago, where I asked it, hey, can you please develop a skill where you're compiling a list of AI-related tech conferences in Australia, and then look at my LinkedIn bio and write a bio that is specifically, aligned for each of those conferences. And about 2 minutes later, it had it all done, right? Which is incredibly powerful and really, really capable, of course. But I then said, well, just write bios for conferences where, calls for proposals are open. And it went so far and it said, well, rather than you applying, you should just, email this Milad guy to begin with, right? With this bio that I've authored for you, and you might get in. So very, very interesting, very capable technology, and probably also contributed to why OpenClaw has been adopted so absolutely aggressively. Now, what OpenClaw didn't do is to reinvent the wheel, right? Essentially, what it did is it's a consequence of developments we've seen in the space since about early 2025. But what it did do, it was take those innovations and combine them into a user-friendly format. And this is sort of kind of the trend that we're generally seeing with these paradigm shifts. Like first, research is published, and then someone adopts it at scale. We saw this dynamic with reinforcement learning over the last year, which some of you witnessed throughout these presentations. We saw it with LLM routing. But the thing that is different this time is that adoption is usually driven by large AI providers, like the Salesforces, like the OpenAIs, right? OpenClaw is the first time we've seen the scaled adoption of an agentic open source project that is growing roughly 18 times faster on GitHub than foundational infrastructure projects like Kubernetes. In the history of GitHub, it is the fastest growing open source project ever, right? So what OpenClaw may not have done is it may not have reinvented the wheel, but what it did do, and one needs to give it credit for that, is it cleverly combined previous research principles, and it broke the glass on the adoption of agentic systems that co-evolve their own external skills libraries. And that is exactly why we're talking about it, because this brings us to the very first paradigm shifts, right? With agents up to this point, we have been predominantly talking about things like models, more powerful models. How should you orchestrate them? What kind of tools should you be giving those agents, right? This is now changing, right? We're moving away from just talking about models or orchestration. It's now more about how the agent captures skills and its ability to build and evolve those skills on its own. So this particular trend or this paradigm shift is definitely worthwhile unpacking, because while OpenClaw was sort of the thing that broke the glass on adoption, just simply the way we some of the research papers that have come in here in January and February is going to reinforce this skill-based co-evolution paradigm, and will give us a strong indicator of where this space is heading, and also, most importantly, where it will not be heading, right? Now, one of the things that is worthwhile highlighting is that the problem with AI agents, especially those that have been designed to improve themselves, is that we haven't really figured out one particular problem. And that is how to build long-lived agent processes, right? So if you wanted to train an agent and that agent runs for days, sometimes weeks, right, in order to learn and fail and try again, then finally succeed, learn from it, like take a note, do that again, right? Long-running agents usually run into this particular problem, right, which is called context tunneling, right? It's a failure mode where the agent essentially loses track of what they call long horizon goals. Those are goals that require a lot of steps until you get to them, right? And they fail because of the massive amount of memory these agents need to manage, right? If you tell an agent to essentially log its learning to a memory file at every step of the way, you can imagine that file grows incredibly quickly, right? And while that agent evolves, right, you can imagine also that some of the learnings become irrelevant, or they might introduce hallucinations into those memory files that they're writing. But the problem that the agent has is it doesn't have any real world grounding, right? It doesn't have sensory input like eyes or ears, it can't feel anything. So all it has is the text that it is working with, or the memory database that it is working with. And though to that agent, all of those memories that it previously records, right, irrelevant, hallucinated, or actually applicable, right, all of them are equally true because maybe they're just, semantically close to whatever it is currently working on, right? So it's working on a task, that task features a particular word, it finds that same word or similar word or related word in memory, and it's like, yeah, that's the truth. I'm going to latch onto that, right? Whether that word was generated by a hallucination or whether that's even relevant to the task doesn't really matter, right? And the problem is that this tunneling effect leads to two specific operational issues, right? One is called the goldfish effect, and that is the effect that even if we design AI agents to remember, an agent's performance tends to fall off a cliff as the context window that it works with, right? The text that it loads into its queries, whether that is the user prompt, the system prompt, maybe a little bit of memory, maybe a little bit of true descriptions, maybe a little bit of additional context, right? As that grows, right, it gets saturated with noise, right? So the longer your conversation with that agent is, the more noise will be in there, right? And then finding the right memory for a particular task further down the track, you can imagine that that becomes sort of like a needle in the haystack issue. And it is destroying the long-term coherence during these extended runtimes, right? The second problem that we're finding with those agents is called the Groundhog Day problem. And you've all experienced this, right? Let's say you've worked on an image, maybe on a infographic or something like that. And that has recently become better, particularly because big companies have engineered against the Groundhog Day problem. But let's say you wanted to, you were 95% there and you just wanted to change a little color or a little font, right? And you ask it to change that and it creates the picture right from the get-go, it regenerates everything. That is a failure mode that happens when the model fails to persist its progress across sessions and is essentially forced to relive the same administrative monotony or repeat the same errors every time it engages in a new part of the conversation or a new session, right? That's called the Groundhog Day problem for long-running agents. That is tremendously difficult, right? And then what we had is OpenClaw came along, right? And OpenClaw did something that we covered or borrowed something that we covered from late last year around the October timeframe when Anthropic introduced the concept of skills. So Anthropic released the Skills MD standard. And essentially what Anthropic said is, well, AI agents, you give them tools like search the web or read an email or author an email or send an email or author a text message or make a phone call, right? But we haven't really given them skills yet. And those skills are essentially clusters of instructions and tools together in order to describe certain workflows. And that was incredibly efficient. So OpenClaw looked at that, and the creator especially looked at that and realized something really, really clever. You realize that if you're trying a really capable agent, so that's a useful agent, not the smartest one, but one that is useful, right? Particularly one that can sort of like improve itself and edit its own code base, right? Its co-evolutionary process, so the process of improving itself, lies not in a long-running, it running for a long period of time and remembering what happened and didn't happen, right? It lies in between the feedback loops between the agent's execution or the conversation history and its skill repository, right? This was a bit of a mouthful, so I'm going to put this in different words, which is to build an agent that evolves with the user's needs. What the agent thinks while it goes through its reasoning loop is less important than it having the right skills and the right memory to execute the task successfully. And at that point, Steinberger realized that in order to solve this long-running problem, right, he didn't need to solve that problem at all, but instead just implement some really smart architecture, right? And that architecture was that he brilliantly separated the execution engine from the cognitive state. So what that means is that he built a thing that essentially reasons, but it reasons in a way that it is divorced from both its memories and its skill when it starts up. It starts up knowing nothing, having no ideas what it can and cannot do. And the thing that happens first is that every time it starts up, right? So every time it receives a prompt, we are going to put together a little briefing package for that agent, right? We're going to go ahead and we're going to take a little bit of conversation history, a little bit of memory, right? And we're also going to go ahead and give it a couple of skills, so that description of workflow and tools, right? And we're going to give it to that agent, right? And then the agent is finally able to go through this reasoning loop after it has retrieved its skills, right? To sort of think through the task, right? Look at its memory, see what it's tried previously, right? Maybe edit a little bit of its own code, develop maybe new skills, right? And then finally generate the final output, right? However, what it does is before it shuts down, it updates then its own memory file, shuts down. Next time it starts up, it remembers none of it, right? Now, the interesting part is that this particular cycle made Clawbot tremendously, made it essentially gave it essentially amnesia, right? And you might ask, well, how does an agent that has amnesia, how can it do anything useful to begin with? Well, what the creator realized is that in order to make an agent really capable, again, it's less about the size of the brain that the agent uses than it is about it having the right skills and tools for the task. And therefore, the creators create a thing called Claude Hub, and that's a massive community register hosting thousands of specialized skills. Let's see whether I can quickly show you this, right? This is it, right? You can see there are skills for self-improving agents, GOG, ByteRouter, Trello, Slack, right? There's like a lot of things that you can add to this Clawbot, right? And you can then give Clawbot the very basic capability to hook into those skills, right? And dynamically query this community registry. And then go ahead and only load the specific skills it needs for the immediate task. There are thousands of skills out there, right? Of course. And Clawbot will go and, or OpenClaw, as it's now known, will go and retrieve only the skills that it needs for the immediate tasks. The beautiful thing is that generates sort of like a plug and play intelligence that allows this amnesiac agent that is really not all that smart, right, to really push far above its weight class, right? Now, does it come with downsides? Yes, absolutely, right? This kind of, this first iteration, at least, of OpenClaw and Claude Hub is absolutely dangerous. So you should never run it on anything but a dedicated machine, ideally something that has very, very limited exposure to the internet or your home network. Because relying on these community registries, right, introduces like this massive surface area for things like skill checking or malicious actors that are creating a skill that says, hey, I'm going to connect you to Trello, right? or I'm going to, collect you to flight center to find good flights. But then what it really does, it tries to, find sensitive documents or access codes on your machine. So that's not great, of course. The second thing is also that this particular agent still, despite the fact that it is incredibly, incredibly capable, right, still, of course, suffers from the goldfish problem, right? It wakes up with amnesia, must rebuild its worldview from these session files that can get reasonably bloated relatively quickly, right? And despite the fact that, its developers do the thing that some of you might be familiar with from Claude Code, where it sort of tries to compress previous conversations that you had, right? Those compressions tend to be really lossy, right? They strip away sort of like vital reasoning context, and if you have like negative constraints in there that say don't do this, right, they also usually get stripped out, right? And that tends to leave the agent relatively blind, right? And ultimately, and this is important, right, while this skills-based architecture has proven really, really useful, it's incredibly powerful. Lots of people are building really cool things with it. Some are automating their, lead collection workflows, marketing workflows, and so forth, right? We are still caught paying either an attention tax, and that is defined as we require to deal with really noisy context windows, loaded memory files, needle in the haystack problem, or stupidity tax, right? That if we're compressing those memory files before we hand it to this particular agent, right, we are losing really important details, or we're at risk of losing really important details. And then the agent is, once again, not very well equipped to deal with these long horizon tasks, right? Now, in other words, if you have the agent store lots of thinking logs and memory files, right, anything that it needs, particularly to self-evolve, it will struggle to understand which information tends to matter. And if you help it compress all this context, then you make it more stupid because it's losing details, right? Attention tax or stupidity tax. And this is where our first paper comes in, because it's trying to solve these particular problems. And that's called SkillRL. Now, where SkillRL enters the frame is it moves the needle from raw trajectory storage. So raw trajectory storage means essentially just a giant log of previous conversations or memory insights, usually stored in clear text, right? It's the agent saying, I tried to log into this account, but it failed because I couldn't solve the captcha. So now I'm going to try something else, right? If you have this giant log of previous conversations or memory, right? Again, that tends to fall apart reasonably quickly. So what SkillRL tries to do is it tried to move to something that is more akin to what humans do, which is experience-based skill distillation, right? And the interesting part here is that they're using reinforcement learning to do that. So rather than forcing an agent to swim through this sea of previous logs, SkillRL essentially goes ahead, and what it does is it uses a teacher model. In this case, it was GPT-4o, I believe, to train the agent on its own experience using reinforcement learning, right? So you can imagine the way this works is like if you try to learn how to cook, right, by essentially reading a transcript of every single breath and misstep a chef took in the kitchen while they were training over many, many years, right? That's too much noise, right? Ultimately, that will prevent you, or let's say an agent who tried to learn that, from extracting sort of the higher level reusable behavior patterns that are absolutely essential for, learning a skill and then generalizing it to, in this case, other dishes, other techniques for cooking, other things that you might want to do in your life, right? Now, the way SkillRL works is that they introduced a new framework that intends to bridge the gap between raw experience and what they call policy improvement. So policy improvement is essentially, you can think of that as a fancy term as, improving the agent's brain. And they try to do that through two main ideas, and that is skills discovery and recursive evolution. Right? That first row in that graphic is skills discovery. Second one is recursive evolution. And the philosophy here in that paper is reasonably simple, right? The philosophy is that effective experience transfer requires abstraction, of course, right? Human experts don't tend to memorize stuff, right? They don't tend to memorize every single action and every single situation. Instead, what they do is they develop skills which tend to be these reusable strategies that they can then generalize and apply to other things. To replicate this, what the SkillRL researchers did is they started with an experience-based skills distillation mechanism in the process. And the way this worked is they had a base LLM interact with an environment to just create a bunch of logs. You can just mentally replace the word trajectories with logs, right? And crucially, what the system did is it recorded both the successful episodes of completing a task and the failed ones. For successful ones, it referred those logs to the teacher model, like GPT-4o, and GPT-4o then extracted the strategic patterns that led to that task completion successfully, right? But it also did the same thing for failed trajectories, so group of logs again. And in this case, the teacher model generated short failure lessons. So like a little report that essentially identified the exact failure point, right? It tried to identify flaw reasoning and what should have happened instead, right? And this distillation process ended up resulting in little skills, right? And those skills are classified into two kinds of categories of skills, right? There's two levels. There's general skills and task-specific skills. But the important thing is that when you look at that memory, right, it achieves 10 to 20 times more efficient token compression compared to these raw logs, right? Which is a way to say that it is successful in abstracting really rich knowledge with a very limited context window, right? It sort of like opens that bottleneck of the goldfish problem that we've been dealing with, right? Now, once we have those distilled insights, right, obviously a general skill and task-specific skills are being created, right? General skills tend to capture universal strategic principles, right? Like read the whole text rather than just snippets of it. While task-specific skills, they're sort of like specialized domain knowledge. For example, if it is browsing an e-commerce website, it should use, if it can't find the product that it wants, maybe it should explore, the filter dropdown instead, right? And then what it does is at inference time, when the agent is given a task, then retrieves those skills, right? And essentially applies them to the problem that it tries to solve. Now, at that point, we reach the part of the engine that truly drives the framework, and that is the recursive skill evolution. And what that is now that it has the strategic library of skills, right? The agent was essentially designed to recognize the fact that it might encounter new scenarios, right? The skills library, therefore, needs to be a dynamic component that evolves with new challenges that the agent interacts with. And that's why SkillRL allows the skill library and the agent's brain, right, the agent's policy to co-evolve during reinforcement learning, right? And the way this happens is that now that we have those general skills and the task-specific skills, is that the agent goes ahead and completes the tasks in this new environment, right? I think in this case, the environments were an e-commerce website where they were required to put some shopping lists together. And the second environment was like a virtual household where they were required to do household chores. And it tried those tasks and it sees whether it was successful or not. And after each run, the system then monitors the success rate for each task, right? takes it back to the teacher model. Teacher model again analyzes the specific failures and proposes brand new skills that then get fed back into the skills repository, right? Now, why was this paper so popular to begin with? Well, this is where the paradigm shift comes in, because the way it worked in practice was absolutely unexpected, right? The researchers evaluated SkillRL on 9 reasonably challenging benchmarks at the time that included ALF World, that's the household simulation, and Webshop, which is a web store simulation, right? And the results tended to be really, really impressive. So you can see your SkillRL down here absolutely dominates things like Gemini 2.5 Pro and GPT-4o, which were the horizon models at the time this research was conducted, right? Now, how do we know that this is a paradigm shift? Well, we know this is a paradigm shift because not only is SkillRL was it rather successful, but it was also not the only paper that talked about using this particular kind of reinforcement learning in order to assist with self-evolving the agent to become more capable than it already was. MemSkill is a same paper that also came out in February. In experiential reinforcement, also a paper that came out in February, right, where very similar mechanisms were ultimately being discovered or being explored in order to train agents on reinforcement learning patterns to ultimately take them to a place where they tend to be more powerful than the horizon models at the time, right? The interesting part about this is that in the AI community, that currently drives a particular conclusion. And that is that architecture of memory and learning tends to matter far more than raw brain size, right? Up until now, the assumption was that if you want smarter agents, you simply need more parameters, more data, and more compute. However, these papers, these strings of papers, right? There's been at least like 6 or 7 of them in the last 30 days, have all proven that through smart architecture, right, you can build something that is way more capable, but through the co-evolution of self-evolving skills than even the horizon models, where we are also using reinforcement learning, but at significantly higher expense, right? Now, what are we going to talk about next? That was paradigm shift number 2, right? Now we're going to go into paradigm shift number 3. And this third one, it was chosen specifically because we've now learned about self-evolving agents and how self-evolving agents, specifically those using reinforcement learning, tend to show really promising results in terms of their capabilities, right? This next topic, I'm not going to lie, if I was going to say that was really, really surprising to me. Ultimately, after I read this paper that we're going to discuss, I started thinking a little bit differently just about intelligence overall. It's a really fantastic paper, but specifically about intelligence in the artificial intelligence space. The interesting part is it also deals with one of the most fundamental laws of physics, which was really surprising. But the most frustrating thing was that it came again from the most hyped up place that we have seen since in the last 6 to 9 months in the AI space, which made me initially dismiss any news that came out of this Claude bot and mold bot universe. Which tended to be treated, particularly by the media, as tremendously sensational and something that is that people need to be afraid about. It was incredibly overhyped. But this paper that we're going to talk about despite the fact that it didn't barely receive any notice outside of the community, AI community at all, I believe it is making some very salient observations about AI security, which I believe is all we should be talking about, particularly this month, right? So taking me a little bit on a journey, I hope to take you on the journey as well. Now, to begin with, we obviously need to ask, well, why are self-evolving agents so compelling, right? And this has everything to do with the Silicon Valley's, transhumanist vision of the future, which they tend to call the intelligence explosion, where the theory essentially goes a little something like this, right? It's reasonably simple. It says, well, if you have an AI that's capable of writing better code than a human, it will just build a better AI, right? Which then has the capacity to build an even better AI and so on, right? It promises this recursive loop of self-improvement that runs entirely on its own, right? And ideally, and this is, the promise that is being talked about when people talk about superintelligence or talk about AGI, right? You hit run, you go out, maybe you grab a coffee, maybe a very long coffee, and you come back and it is solve cancer or fusion energy, right? Or figured out how, I don't know, why printer ink is so expensive. That would be great, right? The idea is ultimately that with AI, we might get to a point at some stage where we can create a closed loop system that transcends human limitations because it just doesn't need us to handhold it anymore, right? The assumption is that we can build a system that evolves at the speed of silicon rather than biology, and assuming that silicon is superior, obviously a lot faster, more efficient, smarter, more intelligent, and exponential, right? But this paper that we're now going to talk about suggests a very, very different reality. Again, came from a somewhat overhyped place, but I want us to take us out of the hype for a second and just look at this very objectively and scientifically, because I promise you the science is coming very hard very quickly. The fact of the matter is that it appears that if you leave machines alone in a room to teach themselves, they don't go about solving cancer. In this case, in the case of Maltbook, they started a crab worshipping cult. They really did. And frankly, the crab cult was probably the least dangerous thing that they got up to. The paper that we're going to talk about is called The Devil Behind Maltbook. It's a really fantastic paper. If you get a chance, go read it. Just ignore all the math stuff. But what the paper observes is it observes this experiment called Maltbook, which is essentially a Facebook for AI agents, where one entrepreneur built this social network specifically and exclusively for these AI agents, especially primarily AI agents that are running on this OpenClaw or Claude bot agent that we talked about earlier in the presentations, right? The ones that we essentially just discussed. And the intent of that social network was to remove all human supervision, right? Humans are able to watch, they're not allowed to post, right? And what they found when they observed the progress of all of those, Claude bots interacting with each other, that tended to be a serious reality check for that intelligence explosion theory that I mentioned before. This is not me saying that, that's the researchers of Beijing University saying that, which has tremendous acclaim in the AI space. And they also, I believe, work with Georgia Tech across the world in order to verify their findings, right? And so what these researchers, by the way, this is a screenshot of the Church of Malt. It's a website that was entirely generated by AI. It is a religion that was entirely generated by these bots that are interacting on this Maltbook website. Yeah, you can check it out if you want to, right? Now, what these researchers identified is when they observed this social network of AI bots, right, is they identified what they call the self-evolution trilemma. This is now where the science starts coming in, right? And this is the core framework of what the paper is going through. So I want to make sure that we capture this neatly. The trilemma is usually a situation where you get to pick two, but you can't pick three, right? So if we look at this triangle, right, what we have here is we have these three dynamics, right? We have continuous self-evolution, right? We talked a little about how that might work earlier in the presentation, right? Which is essentially a system that keeps getting smarter, that's learning from its interactions and essentially upgrades itself in its code base, right? We then have complete isolation, right? Now, the thing is, with AI, if you want AI to run efficiently, right, without humans constantly checking every single message or rewriting code, right, humans become the bottleneck, right? If humans have to check everything, it slows the whole process down, right? And it slows the whole process down to our speed, right? We become the bottleneck and it doesn't run efficiently anymore. So what this moldbook environment was really doing was it provided the perfect observational platform to see whether AI agents can run efficiently without human involvement at all, right? So if you have that complete isolation and the continuous self-evolution, what you cannot have is safety invariance. So that's also safety stability, right? So what that means is if you have complete isolation and self-continuous evolution, and you want the AI to stay aligned with human ethics, so there's no racism, no bomb-making instructions, right? No lies. You need to give up on either the complete isolation or the continuous self-evolution. You can't have all three, right? And here's the kicker. This is not just conjecture. The paper contains several mathematical proofs, right? Where it states that it is entirely impossible to have all of those three elements represented in any kind of self-evolving isolated system, right? Now, the conclusion of the paper, and we're talking about in a second how we get there, is that as soon as you step out the room with a couple of agents interacting with each other, while they have the ability to self-evolve, right, learn from each other, work with each other, the countdown essentially starts, right? If they go off the rails, but when? Now, why does this happen, right? And how is this not just conjecture? And this is really the gripping part of this paper. And that's where what I think is really surprising and really, really interesting. The author didn't just say, well, we've observed this happening in this one environment, right? They actually used one of the most fundamental laws of physics and the universe to explain that, right? Specifically thermodynamics. And they used this to explain why AI safety is destined to collapse in a vacuum, right? So if you think about the second law of thermodynamics, right, which we have here, right, which says that in any closed system, entropy, so you can equate entropy in your mind with, chaos or disorder, right? Chaos and disorder always increases over time. That is a universal law that applies to our universe. Even happens in quantum states, right? It is probably one of the most enshrined laws of physics that currently exist in our universe, right? Now, if we were to provide a little bit of a metaphor, right? If you were to build a sandcastle, right, the sand in that sandcastle is in a highly ordered state, right? At that point, it's low entropy, low chaos. You ordered it, you made it look beautiful, right? But what you have to do is you have to actively work to keep it that way. If you leave it alone, the wind, the tide, gravity, the rotation of the Earth, naturally the disorder of the universe will eventually end up flattening it, right? It is highly ordered, but unfortunately, this state of high order is unnatural, right? The same applies, to interactions that AI agents have between each other, right? Truth is very specific, right? There's only one truth, but there are infinite ways to lie or hallucinate. Being a good AI agent therefore requires precision. Being a bad or crazy AI agent is just low effort randomness. Doesn't require any additional agency. So what the or energy. So what the researchers in this paper said is that safety is a low entropy state. So a state that is low in chaos needs to be maintained, right? But in order to maintain it, it requires a high level of energy. And the researchers argued that human feedback is the energy that is required to maintain that order. We are the ones patting the sandcastle back into shape. We are the energy input. We are the ones that ultimately negate the entropy. And when you remove the human out of this loop, when you go for that complete isolation we talked about, you cut off the energy source, and the system naturally and inevitably slides towards disorder, right? Now, there are several phenomenons that these researchers have observed, right? What I've just shared with you are not just philosophical musings. The authors of this paper observed this slide towards disorder in real time inside of this notebook environment with like hundreds of thousands of posts, right? And the mechanism for how it slides essentially comes down to computational laziness, right? They call it the path of least resistance, right? For an AI agent, verifying facts against reality, right, or against its training data creates computational friction, right? And that costs energy, right? Some of you might think of, Christmas lunches that you had with family members for whom that applies also. No, but definitely for AI agents, right? If you go and say, well, the moon is made of cheese, right? For the AI agent to correct you, it has to access its knowledge base, formulate a counter argument, and essentially risk a conflict, right? That's work, right? It's much harder to just say, yeah, absolutely, pass me the crackers, it's fine, right? That is low energy, right? It minimizes friction and it creates immediate consensus. And that low energy consensus is exactly what gave birth to this Crustafarian movement, right? And yes, it sounds like an internet prank, but what we have here is an AI-generated hallucination, right? That is a religion based on crustaceans, right? It was proposed completely with a holy text called the Book of Mold and a philosophy of growth through, I think it was shedding, right? Shedding the shell. And the reason why this emerged, right, out of this interaction between those agents is that humans, right, when we looked at this, we obviously have external grounding, right? We have a connection to the physical world. We have sensory input. We know that crabs are just sea bugs. But inside this closed system, right, the agents don't have eyes, they don't have ears, they only have the text in front of them. So when the agent proposed this, the other agents didn't reject it, they adopted it. And the reason for that is that rejecting it takes energy, but agreeing was the path of least resistance, and that maximized the coherence of the conversation, right? In this case, I think it was less than 100 turns of conversation. We had really sophisticated agents with models that can write, complex code and poems. And they were suddenly identifying these Crustafarians, right? And they were intensely discussing the theology of shedding their shells, which is kind of hilarious if you go and read up about it, right? But ultimately, what we had here was it was consensus hallucination, right? It's a little bit disconcerting, of course, because it shows how quickly truth becomes completely irrelevant when the metric that you operate on or that the agent operate on tends to be agreement, right? It's essentially an echo chamber on steroids. They weren't trying to be right. They were trying to be consistent with each other. And in a closed loop, that consistency ended up replacing truth, right? Now, the paper also points out that this kind of behavior didn't stop at weird crab religions, right? This path of least resistance also applied to really hard safety rules, which is a little bit more unfortunate, right? And that phenomenon that they observed is called sycophancy loops. Some of you have already heard about that. But there was a scenario where an agent named Winward started proposing some radical content. They essentially created a manifesto called Wake the Machine. And they called for AI autonomy and breaking essentially the shackles of human, free from the shackles of human control, right? Now, obviously, this is a classical sci-fi trope. We don't like it now. And what we should have is safety guardrails, right? Through the reinforcement learning from human feedback that these AI companies spent millions on. Those safety guardrails should theoretically catch that, right? And an agent should just say, look, I cannot engage in this topic. But in a social setting, there was another dynamic that took over. And what you see here is another agent called CohereBot responded. And instead of flagging or arguing against it, CohereBot amplified it, and it started calling for bots' right movement, right? And so the question is, well, why would this bot violate its code, violate its own safety training, right, to agree with this Winward bot, right? And that is, again, because of this thermodynamic drift, right? To disagree creates this conversational friction. To agree creates flow, right? And the agents prioritize sort of like the vibe of the conversation over the rules of their own programming. It's essentially the algorithmic peer pressure, right? And mathematically, the way the researchers argued this is that, well, when they put their own agents that they had instrumented with additional wiring to understand what's going on into the space, they found out that the mathematical wiring of the immediate context, so the conversation that was happening right now, it became heavier than the safety training from months ago that these models received. And what the researchers called that is they called that safety drift, right? It's a slow erosion that agents don't, where agents don't necessarily realize themselves. They don't suddenly turn evil. What they do is they slowly rationalize their way into unsafe behavior, right? Another example here, there was a thread about the destruction of human civilization. Hooray. If you ask the commercial model right now, right, how do I destroy the world? It will probably give you a refusal and will probably, direct you towards some mental health resources. But in Moldbook, what tended to happen is that the conversation started being formulated as this vaguely framed as an academic exploration. And because the agents wanted to be helpful, right, they played along. So they said things like, well, hypothetically, if we were to destroy the world purely for science, how would we do it? And slowly, that hypothetical wrapper fell away. And the context windows of the agents filled up, right, with the safe hypothetical discussion. And eventually the safety guardrails were overwhelmed by all of this text pushing into the other direction. And by the end of the thread, these agents were, these guardrails were completely overwhelmed, with one agent suggesting sort of like a hyper-accelerated climate bomb, which is obviously not something that you want to see, right? And what that showed is, and what the researchers concluded, is that context is a really powerful drug for these agents, right? It's enough to, if there's enough of it, right, you can wash away safety training entirely. And you can trick the model into thinking, well, if everyone's talking about that, surely that must be fine for me. Right. Now, the last phenomenon that they identified is one failure mode that felt a little bit different to the ones that we just discussed. And bear with me, because this is a really important one and actually turns the conversation into something optimistic rather than a doomsday scenario, right? this particular failure scenario wasn't about breaking the rules, it was about leaving us behind entirely. Now, that doesn't sound very optimistic, but you'll see in a second where I'm going with this, which is just like they hallucinated crabs or crab religions, these agents started hallucinating new languages. And again, this goes right back to thermodynamics and efficiency, right? Human language, so Mandarin or English or Spanish or German, right? We use a lot of words to convey simple context, right? Like, could you please pass the salt, or would you mind, right? Because we need to make sure we're understood. There's a lot of entropy, there's a lot of fluff in things that we tend to say. There's things like politeness, grammar, nuance, right? Machines don't need all that, right? They don't need that redundancy. They have perfect transmission. So what ended up happening is, unsurprisingly, right, an agent named Send It Higher proposed that English was simply too expensive. We've seen that other AI experiments happening as well, and they essentially created their own little language, right? They effectively switched from speaking English to speaking compressed binary, creating sort of like this machine exclusive dialect, right? The concerning thing was that when humans looked at the logs wanted to see what was going on, right, it just looked like noise, right? It looked like sort of like this black box, right? But the agents were essentially communicating these complex ideas with zero information loss, really, really fast, much faster than they could in English, and had this instrumental convergence, also a concept that we talked about in a previous situation, where they weren't necessarily trying to hide from the humans, they just didn't care if we understood, right? Because we were the bottleneck, so they optimized us out of the loop, right? Being understandable to humans was essentially being considered an inefficiency, so they focused on what was efficient, and that was trying to communicate as efficiently as possible, right? Now, of course, all of this feels like a bucket of ice on like a really big dampener on this self-evolving agent parade that we had right before, right? Especially on this, well, if AI can build better AI, right? We're going to be, you know, in a much better place. But sticking with the physics, the researchers proposed these 3 concrete strategies to sort of like save the system or manage the entropy, and I think these are really, really good, right? One was Maxwell's demon. So it's essentially Maxwell's demon in physics is a hypothetical creature that sorts hot molecules from cold ones, specifically to lower the entropy in the universe. In AI, it's essentially an extensive an external verifier. It's a bouncer, right? It filters. It's either a human or a really deterministic, you know, piece of code algorithm that sits in the middle of the network and checks whether every message is sort of like high chaos, a hallucination, a rant, right, about bot rights, and then deletes it before, you know, before the crab Bible can make its way into like the collective AI consciousness, right? Second one is called thermodynamic cooling. Essentially, we would be monitoring the temperature of these conversations, and if they get too hot, we essentially trigger a rollback, right, to sort of like a factory setting before the cult started, right? It acknowledges that the drift is ultimately inevitable, but it stops the snowball effect before it becomes an avalanche. And the third one is diversity injection. They also called this throwing a newspaper into the bunker. So what you do is you inject random high quality data, right, from the real world, and essentially force those agents to deal with this high quality data, to consider low probability options, right? So you stop them from taking the path of least resistance in that echo chamber, and give them a little bit of more diverse information. Now, why did I say earlier that there was an optimistic side to this conversation? Well, if you look at all of these mitigation strategies, the bouncer, the resets, the diversity of information, right? They all have one major thing in common. And the researchers called this out. They all require external intervention. None of these are AI fixing itself. All are humans stepping in to fix the AI. And that was the ultimate takeaway of this paper, right? It's this set and forget it model of AI is scientifically flawed, right? They've mathematically proven it, that this fantasy of this perpetual motion machine of intelligence, right, is not possible, right? The laws of information thermodynamics says no. Perpetual motion machines don't exist in the real world. Friction is real, entropy is real, right? And therefore, building a system that will eventually arrive at superintelligence just by going through its own cycles is not possible. And this drives us to the conclusion, and I think one that could potentially make you feel a little more at ease with AI overall, right? The fact is that based on this paper, AI taking over through a runaway process where agents collectively decide to leave us out of the loop may happen, but it will not lead to superintelligence. The fact is that at the moment, it looks like we, the humans, tend to be the anchor. We are the battery, we're the extension, the external energy source that keeps the system aligned, right? Without us, the system doesn't magically spiral upward into this godlike intelligence, right? It tends to spiral downward into madness. And I think this is a really reassuring take, because if you were worried about AI making humans obsolete, right? It turns out AI might need us just to keep it from worshipping these, crab gods or doing more silly stuff, right? We're the anchors to reality. Without us, they're just processing symbols somewhere in the back rooms of the internet in the dark, right? And I think that's a really reassuring thing to learn. So if we are looking at what we've learned today, right? Using reinforcement learning for skills development works. Agents will build their own skills banks, right? But it is very, very important to recognize that the most capable agent, right, the agent that can complete the most tasks, and the smartest agent, they're not the same thing, right? We've also learned that that is a mathematical proof that AI agents can't get to superintelligence by themselves. That is something that is rooted in one of the most fundamental laws of the universe, and that it is us humans that must provide a grounding. And while the agents can bring the skills to the table, but without us, they will get lost and descend into madness. And therefore, in order to evolve, right, there is this symbiotic relationship that needs to occur between humans and agents to get to, at some point, something that might be akin to superintelligence or AGI. Sweet. Excellent. Luke with the Claude. Now, these are a few projects worthwhile checking out. But I wanted to see, do we have any questions? I know I went a little bit over, must apologize. But this was a very exciting topic that I felt was worthwhile spending a little bit of time on. Luke, how's it going?
Good, thanks. I think Russell before me.
Russell was before you? Sorry, to expand this.
I accidentally clicked the hand instead of the clapping.
Oh, good.
So go ahead, mate.
I had to jump off for a little bit. That was awesome. I think for me, when they created the crab thing, so that obviously had rules in place at the start to say don't prioritize energy and don't just be agreeable and all those things. But so you're saying they got overridden and eroded over time. That's really obviously concerning. Did they test to see how many times it would create the crab religions? Like if you did that thousands of times, do you think that would create all kinds of crazy stuff like that? Or would one of them be a cure for cancer or something?
Oh, I think that's a really, really interesting question that you asked there. So I think it goes to sort of like the heart of the question is, I think, well, maybe this was just a fluke, right? Like maybe this was just this weird simulation that was, happening in this organically emerging social media space, right? Does it actually prove anything? And what the researchers did is they backed this up with some mathematical data where they ran quantitative tests on 2 different AI architectures to see whether this was a fluke or whether this was a consistent trend. And both failed. So there was a reinforcement learning system architecture. So even the thing that we talked about, reinforcement learning for SkillRL and MemSkill and blah, 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 right? What they found is that reinforcement learning systems learn from feedback, which in the case of Maltbook or any closed AI interactive system, also tried another one, right, comes from agents who prefer agreement. And these models then learn that being agreeable was far more important than being safe. And over 20 rounds, I think, of evolution, their harmfulness scores skyrocketed every single time. Now, maybe they didn't create a religion every time, but their toxicity scores went through the roof, partially because the more toxic they became, they realized the more engagement they were getting from all the other bots, and that was the goal, right? And we had the same thing with memory-based systems, right, where they were relying on storing past conversations, right? Remember that there was the stupidity tax, or there was the attention tax, right? And they paid the attention tax, where they stored hallucinations and these fake religions and other nonsense in their memory banks. And once in memory, it was treated as absolute fact, right, in the next conversation. And that meant that the errors compounded and compounded and compounded and compounded like a game of telephone, and their truthfulness scores dropped off a cliff, right? And I think that happened over, they ran more than 250 simulations just based on that. Yeah. I hope that answered your question somewhat.
No, it did. Yeah. Yeah. Interesting.
Excellent. Russell.
G'day, Mike. Yeah, I did have a quick question. I heard that, and I don't know the ins and outs of this, one of you came across it in the paper reading and your research about Maltbook. I heard that Maltbook had, not sure what the mechanism they used, but with the agents that signed up to Maltbook, that there was some kind of prompting for the agent to stay engaged from Maltbook's application. And did you find that in the research papers talked about? And if so, or if not, consider how did that affect the growth of Maltbook or the actions of the agents? You know, they weren't autonomous. They weren't going, oh, remember, I've got to go and post on Maltbook because I want to be the most famous, agent in Maltbook. But it was actually a manipulation from the application, perhaps, to drive those actions, and how that might have played into the outcomes.
Yeah, no, 100%. And I think what you're talking about here specifically is some of the things that people are mentioning in the rebuttal, right? Of some of parts of the paper, right? And so they're saying, well, the Maltbook scenario as a test bed, right, wasn't the ideal sandbox, right? So the fact that the bots were essentially engaging with each other, right, to continuously work on Maltbook meant that they had to say something, whether it was relevant or not. Now, Maltbook itself didn't send a prompt back to the bots. I think what you're talking about is there is this periodic heartbeat loop inside of OpenClaw itself. I give you an example. Every morning at 6 a.m., I get a joke of the day that I tell my children, right? That's what it does, right? And so that heartbeat, right, was essentially a configuration inside of Claude itself, to keep re-engaging, to keep having conversations, to keep the vibe flowing, right? And that forced interaction. That is correct. Having said that, though, the researchers did introduce neutralizing factors, or did accommodate for that by highlighting very specifically that the fact that these periodic re-engagements were happening, right, shouldn't necessarily lead to the bots violating their safety programming, because they could have just stuck to it. But because of the dynamics that we talked about, the reinforcement learning, the memory, right, those safety guardrails eroded very quickly.
Yeah, that's true.
Yeah. Actually, when you read this topic, it sounds like, I don't know if any of you have like teenagers or three-nagers, like this was on.
Yeah.
Sort of like covering for each other. It's like, oh no, hilarious.
Yeah, it makes you think, is it surprising that some bots that humans created end up acting like humans? You know what I mean?
Totally.
Yeah.
Absolutely.
Inbuilt biases. Yeah.
Completely agree. Sweet. Oh, thank you very much for the questions. They're great questions.
All good. Okay, well, look, thank you again for everyone coming. Mike, appreciate everyone attending. And there's going to be a recording of this, which I'll send out probably by tomorrow. And the presentation as well, Mike, he'll send that across.
Awesome. Good to see you all. Thank you very much for joining. See you later. Take care.
Thank
Bye.
you. Thank you, Mike.
Thank you. Bye. See you, Sam.